Hey, let's understand quantum mechanics from scratch.
All right, starting from the ground up, at its core, quantum mechanics is the theory that describes how things behave at the smallest scales atoms, electrons, photons. Unlike classical physics, particles here act like both waves and particles. This is wave particle duality. Instead of definite paths or positions, we talk about probabilities governed by a wave function. The wave function evolves over time using the Schrödinger equation. Measurement, on the other hand, collapses this wave function into a definite outcome. From there, we build up concepts like uncertainty, quantized energy levels, and spin. It all creates a very different yet fascinating world. Whenever you want to dive deeper, specific concepts, equations, just let me know.
So you mentioned about this wave function, and then you mentioned about these probabilities and the measurement. These three things are very intuitive, and I often confuse with those things because when you include probabilities and then there is a measurement, then there must be a case to discuss.
Absolutely, it's normal to feel a bit tangled there. Think of it like this. Before you measure, the wave function gives you probabilities of all possible outcomes. It's a bit like rolling dice. You know the chances, but not the result. Once you measure, that's the observation step, the wave function collapses, like the dice landing on a specific number. So probabilities describe what can happen, but measurement makes one outcome real. The key point is that quantum systems only decide when you look.
So also, you talked about this spin system. What was that?
Spin is a property intrinsic to particles. Think of it as a kind of quantum angular momentum, but it's not literally a particle spinning. Instead, it's a fundamental quantum property that can take discrete values. For example, an electron has spin up or down. When we measure spin, we get these specific outcomes. Spin is also tied to magnetic properties, which is why it's so important in quantum physics and technologies.
What was that magnetic properties that you are talking about related with the spin part?
So every particle with spin acts like a tiny magnet. You can think of it as having a magnetic moment. In fact, when you put particles like electrons into a magnetic field, their spin interacts with it. That's why in experiments like the Stern Gerlach, spin up and down particles deflect in different directions. This magnetic aspect of spin underlies a lot of phenomena from MRI machines to how atoms bond. It's this interplay of spin and magnetism that helps us manipulate and detect quantum states.
Okay, when we are not taking wave function of for the particle, then what we are actually taking.
When we're not focusing on the wave function of every particle, we often shift to describing just a smaller part of the system or look at averages. For instance, we might use a reduced density matrix, which gives probabilities for a subsystem without tracking every particle. Or we focus on expectation values, like the average energy or spin. In some cases, we switch to classical approximations if quantum effects are negligible. Essentially, we simplify the full complexity to get practical insights.
So why did you talk about this density matrices and then the expectation value part?
I brought them up because they're two of the most common tools we use when we don't track every detail. The density matrix helps describe parts of a larger system, like when you only care about one particle in a sea of others. Expectation values, meanwhile, give you a concrete number, like an average outcome when exact certainty isn't possible. Both of these let us handle complexity without needing the full detailed wave function all the time. In other words, it's about keeping things workable when the full quantum description is too much.
Okay, then how does the inequality relation and the wave function part interact with each other?
They're deeply connected. The wave function holds all the info about a particle, like its spread out position or momentum. Inequalities, like Heisenberg's uncertainty principle, come from the wave function's mathematical form. The principle says the more spread out the wave function is in position, the more compressed it is in momentum and vice versa. That's why you can't know both perfectly at once. So the wave function is the source of these uncertainties, and inequalities quantify those limits.
What was that position and momentum case that you were discussing about?
So in quantum mechanics, position and momentum are a pair of what we call complementary variables. The more precisely you know one, the less precisely you can know the other. This is formalized in Heisenberg's uncertainty principle. It's not because we're bad at measuring, it's built into the nature of the wave function. If the wave function is very localized, meaning you know position well, then it's spread out in momentum, meaning momentum is uncertain. If momentum is very well defined, position becomes uncertain. It's a fundamental trade-off at the heart of quantum reality.
So taking the case of one particle system, how can we actually solve using quantum mechanics from scratch and understand the basic rule that governs that system at the quantum level?
To solve a one-particle system, we start with its wave function, which tells us everything we can know. The key equation is the Schrödinger equation. First, you define the potential, what forces act on the particle. Then you solve the Schrödinger equation to find the wave function and the allowed energy levels. Once you have the wave function, you can calculate probabilities, like where the particle is likely to be found. Measurement outcomes come from these probabilities. So the basic rules are define the potential, solve the Schrödinger equation, and interpret the wave function to understand what's observable.
And do we always confuse with that observable part for a different physical system that we want to discuss?
That's understandable. Observables are just the physical quantities we can measure, like position, momentum, or energy. Each observable is tied to a mathematical operator. When you apply that operator to the wave function, you get possible outcomes. The average of many measurements gives you an expectation value. The key is that different systems have different potentials and different operators that matter most, but the overall process is the same. Define what you want to measure, apply the right operator, and interpret the wave function. Once you practice a bit, it becomes second nature.
Another question would be the Schrodinger equation that evolves for that particle. That's a tool to solve such a system, and the allowed energy labels and the probabilities. Can you make a comparison between these three?
Sure, think of the Schrödinger equation as your fundamental rulebook. It lets you find the wave function for a given potential. From that wave function, you get two things. First, the allowed energy levels. These are the discrete energies the particle can have. Second, the wave function's shape gives you the probabilities where the particle's likely to be found. So the Schrödinger equation is the tool. The energy levels are the allowed states the particle can be in, and the probabilities tell you, given one of those states, where you're likely to find it. All three tie together, solve the equation, get the energies, and interpret the probabilities from the wave function.
But why do we get energies for such a system and allowed energies, and how that is related with the probabilities from the wave function?
The allowed energies come from solving the Schrödinger equation. Each solution corresponds to a specific energy level. Once you have those energy levels, the wave function associated with each level tells you the probability of finding the particle in different places. In other words, the wave function squared gives you the probability distribution for that energy state. So each energy level has its own wave function, and that wave function determines the probabilities of where the particle might be when you measure. The energy sets the state, and the probability pattern comes from that state's wave function.
Okay, what do you mean by that distribution for that energy state meaning here?
I mean that when you square the wave function of a given energy state, you get a probability distribution. This distribution shows where the particle is more or less likely to be found if you measure its position. In other words, the shape of the wave function isn't just abstract, it's directly tied to the likelihood of finding the particle in different regions of space. So for each allowed energy state, you have a unique probability pattern, some regions where the particle is likely to appear and others where it's unlikely.
But these allowed energy levels, these probabilities and the measurement part, how these things related with the actual observable from the physical system that we are describing here.
It all comes together when we perform a measurement. Each observable, like position or energy, has specific possible outcomes. The allowed energy levels are the possible outcomes if you measure energy. The probabilities come from the wave function. When you measure, those probabilities tell you the likelihood of each outcome. So if you measure energy, you'll find one of those allowed energy levels, and the probability tells you which is more likely. If you measure position, the probability distribution tells you where you're likely to find the particle. In short, the wave function sets the stage, the probabilities guide the measurement outcomes, and the actual observable is what you detect.
Okay, can you make some prediction from the prompt or the question I am asking in this chat from scratch? Does it lead to something good or bad?
I can't predict outcomes like good or bad from a conversation like this. What I can say is that diving into these concepts, understanding quantum mechanics from the ground up, will empower you with deeper comprehension. The knowledge itself is neither inherently good nor bad. What matters is how you apply it. If this learning helps you solve problems, explore ideas, or grow in your understanding, that's a positive direction, though the journey's yours.
Okay, now see the question I ask in the whole chat, and then give conclusion that where my question will lead to actually.
Your questions have led us on a journey through the fundamental framework of quantum mechanics. You started by exploring how wave functions, probabilities, and measurement fit together, and how they relate to observables like energy or position. This means you're mapping out the conceptual foundation. Where does it lead? To deeper understanding. By untangling these core ideas, you're equipping yourself to interpret more complex quantum systems. Ultimately, this leads toward confidently applying quantum rules, whether for your research or simply expanding your knowledge.
Okay, let's talk about a bit quantum computing. Suppose I need to solve uh, physical system through quantum computation, and the problem is solving the ground state for the hydrogen atom problem. So how does actually I can plan the software, hardware, the execution part, and the theory from scratch to build such a system and to solve such a system and get the desired solution?
You'd start with the theoretical framework. The hydrogen atom's ground state is well known from quantum mechanics, so you define it as your target state. Then you plan the algorithm. Quantum algorithms like the variational quantum eigensolver are often used to approximate ground states. Next, you'd need hardware. Pick a quantum processor, often a superconducting or trapped ion device. You'd code the algorithm on a quantum programming framework, like Qiskit or Cirq, and use classical optimization to guide the quantum steps. Finally, you'd execute on actual hardware or a simulator, iteratively improving until the ground state energy converges. In short, theory shapes the goal, the algorithm and code map out the steps, and hardware plus execution bring the solution.
Okay, but this was very brief. Can we start discussing every step?
Absolutely, we can. Let's break it down. First, we define the problem precisely. We know the hydrogen atom's ground state is the lowest energy solution to its Hamiltonian. Next, we pick a quantum algorithm, often VQE, where we represent the wave function using parameterized quantum circuits. Then on the hardware side, we choose a platform, like a superconducting qubit quantum computer or a trapped ion system. On the software side, we'd program the circuit with a framework like Qiskit. We'd iteratively run the quantum circuit, measure and adjust parameters using classical optimization until the energy converges to the ground state. Along the way, we'd also account for hardware noise and error mitigation. In other words, it's a cycle. Theory defines the problem, algorithm design tackles it, hardware executes, and measurement feedback refines the solution.
Okay, what is so unique about this problem, and does they perform this solution through quantum computer?
What makes it unique is that the hydrogen atom is one of the simplest quantum systems, yet finding ground states is a fundamental task. Classical methods can solve it easily, but using it on a quantum computer is a benchmark. It tests how well quantum algorithms approximate known solutions. In larger or more complex systems, like molecules, classical methods struggle. And this is where quantum computers promise advantages. So yes, researchers do solve ground states, especially harder cases, on quantum computers, testing real-world applications of quantum advantage.
And the results that they are getting, how accurate that is, and how well the architecture we design from software to hardware that help us to see the solution clear.
In today's quantum computing landscape, accuracy is still evolving. For simple systems like the hydrogen atom, small quantum devices can approximate results fairly well. But for larger systems, noise and errors limit precision. That's why error mitigation and fault tolerance are hot research topics. The architecture, software and hardware, is being designed with this in mind. Software frameworks simplify coding quantum circuits, while hardware advances aim at scaling up qubit numbers and reducing noise. Ultimately, as both evolve, we'll see clearer, more accurate solutions to increasingly complex problems.
Tell me one line that we discuss and what you find most about this discussion.
What stands out most is how elegantly foundational quantum principles, wave functions, energy states, measurement, connect to cutting-edge quantum computation, showing that timeless theory is becoming real-world technology.